Hi there, long time not see, guys. Today I want to talk about linear programming, which is also referred to as operative research, according to which university you are actually attending. And I want to show you a way to solve the linear programming problems. Generally, at university, one of the things that are shown is the graphical way to solve those problems. However, the graphical way only really works in 2 dimension. If you go to 3 dimension and so on, there is no easy way to solve this. So what I want to show you is the linear algebra approach to solve the linear programming problems. So in linear programming, you always have a problem that you have to maximize or minimize. So let's start with one. Let's suppose that we have this maximization problem. So maximization 2x1 minus x3, and we have x1 plus x2 less or equal than 3, x2 minus x3 less or equal than 0, with x1, x2, x3 greater or equal than 0. So this is actually our problem. Now, for this very problem, what we're going to do is to rewrite this, those two as a simple equation. First of all, we're going to rewrite them as equation, and to do that, we're going to have to introduce those slack variables. So what is it as slack variable? So a slack variable is a variable that is essentially made up. We made that up ourselves, and we have to, if this one is less or equal, the variable is called a slack variable, and we have to add that variable. If this one was greater or equal, then we're going to have not a slack variable, but a surplus variable, and we're going to have to subtract that variable. What I mean by that is that we're going to rewrite this as x1 plus x2 plus, since we have x3 here, I'm going to add x4 because we have the less or equal, so it's a slack variable, and we're gonna say, okay, equal to 3. So we no longer have less or equal, but we have an equation, normal equation. And we're gonna do the same for this other one. So x2 minus x3, we're gonna add, because we have less or equal, x5. So x2 minus x3 plus x5 equal to 0. So again, if for instance we had a greater than instead of less than, then we will be rewriting it as minus x4 and minus x5. So those are called slack variable. If you subtract them, they're called surplus variable. Now, of course, with x1, x2, x3, x4, and x5 all are greater or equal than 0, because we already have x1, x2, and x3, and of course, these two variables that we introduce are going to have to respect the very same condition. Now, we're going to write the coefficient matrix. So what I mean by that is that I'm going to write a matrix in which I'm going to write, which is going to have the coefficient of those variables. So 1, 1, 0, because there is no x3 here, then 1, and then 0, because there is no x5 here. So again, we're going to have that as 1, 1, 0, 1, 0. And here we don't have an x1, so we start with 0. We have an x2, so we put a 1. We have a minus x3, sorry, so we put a negative 1. We don't have an x4, so we put a 0. We have an x5, so we put a 1. And this is our coefficient matrix. Now, we're going to have to choose a submatrix, and we're going to call this B, and the rest is going to be our AN. So our matrix B, I'm going to choose, you can choose anything you want, technically, but you're going to have to see whether you're going to see why I'm going to use that. You can choose this one and this one, or this one and this one, this one and that one. It doesn't matter really. But of course, according to which one you're going to choose, you're going to get different results. So you may have to start again. So for this problem, I'm going to show you that my submatrix B is going to be made by those two, and I'm going to take the rest of them as my submatrix AN. So you always have to pick a B, submatrix B, and everything you don't pick goes to AN as a submatrix. Now, so our matrix B is 1, 0, 0, 1. There is a reason why I picked that, is that it's essentially the identity matrix, so it's very easy to deal with. Now, what we're going to do, we're going to have to find the inverse of this matrix, so B to the negative 1, so the inverse. But this is just the identity, so the inverse of the identity is the identity. So, with what we know about linear algebra, so if you don't know how to find the inverse, just go to the video I made, several videos I made about linear algebra. Now, we're going to have to find our vector B. Now, the vector B is given by those two scalars, so those two numbers. So essentially, the two numbers that we had at the beginning of in the problem, and that we're going to have in the equation once we have added the variables of slack. So the vector B is going to be 3, 0. So essentially is 3, 0. Why we're going to need the vector B, you're going to see in a second. Now, we're now going to find our solution, our base solution. So our base solution xb is given by b to the negative 1, so b inverse, times our vector b. So in our case, xb is given by 1, 0, 0, 1 times vector b, so 3, 0. Now, if we multiply that, we're going to have 1 times 3 plus 0 times 0, 0 times 3 plus 1 times 0. I'm going fast because I assume you already know how to multiply matrices in linear algebra. If you don't, please check the video that I made about linear algebra. So 3 plus 0 and 0 plus 0. So, in the end, we have 3 and 0. Because anything multiplied by the identity always gives the matrix back. So what we're interested in right now is if this solution, this base solution, is greater than 0 or greater than equal to 0. So if it's greater than 0, it's fine, it's better, because it's going to be better, but what we are really interested in terms of base solution is that this one is greater or equal to 0. This is essentially greater or equal to 0 because 3 is greater or equal to 0 and 0 is of course equal to 0. So this is fine. The base solution can be acceptable, and we're gonna go on because we know that those two are greater than or equal to 0, greater than or equal to 0, and which means that it's fine. But we want to know whether it's an optimal solution and not just a base solution, which can be admitted, which can be fine. So to see whether it's the optimal solution or not, we're going to pick the vector. We're going to pick the vector x1, x2, x3, x4, and x5. This vector is made of, well, here. This vector is made of the coefficient of our maximization problem. So in this case, 2, 0, because we don't have an x2, -1 because we have an x3, and then 0, 0 because we don't have x4 and x5 as we have just added them and they're not here. Okay, so the vector is going to be 2, 0, -1, 0, 0. Now, what we're going to do with this vector? Well, we're going to define CB. So CB is made by what we have picked as the matrix B. Now we have picked the first one and the last one. So the first one and the fifth one. So CB, our new matrix, is going to be made by the first component of this vector, so 2, and the last component of this vector, so 0. So it's going to be made by 2 and 0. Now, we are going to define Cn, a new matrix, again, as the component of an of this vector. So for an, all the other that we didn't pick in B were the second, the third, and the fourth one. So they're going to be the second, the third, and the fourth one. So 0, -1, and 0. So the second, the third, and the fourth component of this vector. So 0, -1, 0, 0, -1, 0. Now, at this point, what we're going to do is to find a new Cn, which we're going to call Cn first, which is going to be given by Cn minus Cb times B inverse, so B to the -1, times An. And I want to verify that this whole thing is less or equal than 0. Because if it's less or equal than 0, then it means that our base solution not only is acceptable, as we already found out, but it's also the optimal solution. So it's not just a base solution, it's an optimal solution. And we're interested in that to solve our problem. So now it's just a matter of making calculation, the matrix calculation. So Cn is 0, -1, 0. We have to subtract Cb, which is 2, 0. We have to multiply the inverse of B, which is the identity. So 1, 0, 0, 1. And we have to multiply it by An, which is this matrix here. So 1, 0, 1, 1, -1, 0. So multiply by An, which is 1, 0, 1, 1, -1, 0. Now, if we do that, what we get is, well, we have 0, -1, 0, minus 2, 0, and then we're gonna multiply these by that, and this one is essentially, anything multiplied by the identity gives the matrix back. So we essentially, what we want to do is multiply this one with this one. So 1, 0, 1, and 1, -1, 0. Now, let's go on and try to find this. So Cn first is essentially 0, -1, 0, minus, well, if we do this multiplication, we're going to get 2 times 1 plus 0 times 1, 2 times 0 plus -1 times 0, and then 2 times 1 plus 0 times 0. So Cn first, again, is 0, -1, 0, minus 2 plus 0, 0 minus 0, which is hilarious, 2 plus 0. Okay, and we go on, so we have Cn first, which is 0, -1, 0, minus 2, 0, 2. So if we keep going on, what we're going to get is, first is, well, we just have to subtract, so we get 0 minus 2 is -2, -1 minus 0 is -1, and 0 minus 2 is -2. So all of them are indeed less or equal than 0, so this solution is the optimal solution. So this solution here that we have found is not only acceptable, so not only works, but it's the optimal solution, it's the best possible solution that we want to find. So again, as a very quick recap, what you have to do whenever you find a linear programming problem is to rewrite those as a simple equation by watching whether they are less or equal or greater than or equal. If they're less or equal, you add the slack variable. If they are greater, you subtract the slack variable. What slack means, or surplus, the surplus variable. So what slack variable means, or surplus variable means, is that you just insert 2 new variables. They're not there, they're just made up. At this point, you write the coefficient matrix based on the coefficient of all those variables. At this point, you're gonna pick a submatrix called B, and all the other values are gonna be making another matrix, which is gonna be called AN. So you invert the matrix B with the linear algebra calculation if it's anything other than, the identity matrix. In this case, it was easy because the inverse of the identity is the identity. And you pick the vector B, which is given by those 2 values that are, on the right-hand side of the equal. So this is the vector B. At this point, you're gonna have to find a base solution, which is given by the inverse of the submatrix B times the vector made by those 2 values. And you wanna check if it's greater or equal than 0. If it's not, it means that this is not admissible. It can be, it can't be used. The space solution doesn't make sense. If it is, it means that it's fine. It is a solution. The space solution is indeed a solution, and you want to see whether it's optimal, the optimal solution or not. To find the optimal solution, you're gonna have to find another matrix which is called CB, which is going to be made by the terms of that make the submatrix B, so the first in the coefficient matrix, so the first and the last one in this case, so, and corresponding to the components of this vector, the vector made of all the variables, so all the variables in the maximization problem that you have here. So in this case is the first and the last one, so the first and the last one. Same goes for Cn, which is made by the the component, the corresponding component of this vector, according to which terms have been selected to make the AN matrix, which is a matrix made by everything other than the B matrix. So the second, the third, and the fourth one. So the second, the third, and the fourth one. So 0, -1, 0. At this point, you're going to find a new Cn first, which is made by Cn, which you have just found, minus Cb, which you have just found, times the submatrix B inverse times AN, which is the matrix made by the submatrix made by everything, which wasn't picked up by B, and you want to find whether it's less or equal than 0 or not. If it is, it means that the B solution that you already found, that you verified that is mixable, I mean that is fine, that is a B solution, not only is a B solution but is also optimal. If it's not, it means that it's not optimal. It's still a B solution, but it's not optimal. So you make the calculation and you verify that. So yeah, I mean, we are done. This is pretty much it. I mean, it's not hard. You just, you just have to make a few linear algebra calculation and memorize a few things. But those are, I mean,